Good afternoon. So today is our lecture 4. Before our lecture, I would like to share with you the arrangement of assignment number 1. I think you in total around 4 to 5 assignments to you to help you understand the theories and how to apply the equations. For assignment number 1, in total we have 7 questions. So in fact, for the first 3 questions, I just want you to understand. So for the work, reversible work, was the meaning, and also why in the future we know for expansion process, the reversible work is the minimum. However, for compression process, the ideal work input is the minimum. Okay, is the minimum. This is minimum. Reversible expansion work is the maximum. However, for the compression process, is the minimum. Okay, and then also again, because we know for the compression expansion process, it follows polytropic polytropic process. So we try to understand for the different value of n. So how it varies, not only with the final results, but what's on the pressure volume diagram. So we can share and indicate the difference. And as we have introduced last week, so for these 2 questions regarding the application of first law of thermodynamics, and for question number 6, I'm asking you to understand if the state is in the wet region is a mixture of saturated liquid and vapor, then the dryness fraction and how to calculate other properties, okay, to understand it. So this is the assignment number 1. I think it doesn't take a long time. Maybe this week, today and tomorrow, you can complete the assignment and submit the assignment before Chinese New Year, okay? Just worry about maybe some of you will forget to submit because that's online. So even, and also for the in-class quiz, I will grading it very soon, next I think after Chinese New Year. Any question on the arrangement of assignment? So these 2, mainly first law. This is the first law. And for question number 5 is calculate the dryness fraction and find out the enthalpies and other properties of the state in the wet region. Okay, for the first 4 questions, so they are regarding the calculation of work for a reversible process. And to understand, so if for actual process, then it means irreversible process. Any question? If you don't have any question, then we will start our lecture today. And we remember that for this subject, we have 4 laws. the zeroth law, the first law, and the second law, and the third law of thermodynamics. And in the past 3 weeks, we learned how to apply first law in engineering problems. First law. And also we understand, in fact, for any pure substance, it can undergo thermodynamic process. So with the property changes, so including there is a phase change. So for us, for this subject, we have interest in liquid and gas. So therefore, we are interested in the phase change from liquid to vapor or from vapor to liquid. And we also understand for the property is very interesting because there is a wet region, okay? There is a wet region. So if any state in the wet region, okay, is saturated, and how to calculate the property, how to define if it's in the wet region, we remember how to define the state. So because we can compare like its enthalpy and entropy. So with the two typical, okay, these two typical points. Okay, from the tables, saturated table, we can find the enthalpy of saturated vapor and saturated liquid. Then we can compare with them. Okay, so we know if a state is in the wet region or if it's superheated. And then we know, in fact, in the future, why we always introduce here, that's because for this subject, we mainly have interest in the relationship between heat and work. And we know if we want to achieve the energy transformation, we need heat engines. Okay, if we need energy transformation, we need heat engines. For example, like thermal energy to power, okay, to electricity, like a power plant, we need heat engine. And also for our air conditioning, if we want to extract heat from the colder, lower temperature reservoir and reject heat to the high temperature thermal reservoir, and we need reversed heat engine. Okay, so that's the reason. So for those heat engines, we mainly make use of the pure substance. So for power plant, the working fluid is water steam. And so we are trying to make use of the phase change. During the phase change, the large amount of heat rejected or absorbed, try to make use of the phase change. During the phase change, the heat absorption or heat rejection. Okay, so what we will learn today, we will introduce a second law of thermodynamics. And we also understand anytime any thermodynamic process, it has to comply with both first law and the second law. And we have to relate the second law to energy values. We understand that energy has its quality and value. And we need to understand, so for all thermodynamic processes, there is its direction. So we want to further investigate the different expressions of the second law. And sure, so we want to understand, expand the second law for all reversible heat engines. So let's refresh. We remember, so for first law, in fact, is energy conservation, and it means energy cannot be created or destroyed. It can only be transformed from one form to the other. So for the second law of thermodynamics, it asserts that all the thermodynamic process occur in a certain direction, and that and also energy has its quality and has its value as well as quantity. So all the time, we always need to remember a process cannot take place unless it's satisfied with both the first law and the second law of thermodynamics. So now let's have a look to understand energy has its values. So as we have introduced in our first lecture, thermal energy is special. Okay, thermal energy is special. So other form of energy can be converted, transformed into thermal energy easily. However, so thermal energy is special. Thermal energy is special. So just like as we we have introduced in our first lecture, so thermal energy, other energy forms can be converted to thermal energy easily. However, it's difficult to transform thermal energy into other form of energy. For example, okay, transferring heat to a wire will not generate electricity. Okay, so if you just heat the wiring, it cannot generate electricity. And also, a cup of hot coffee, you want to, like the coffee is hot, the room is cooler room. So the heat transfer is from the hot coffee to the cooler room. However, if you want the hot coffee get hotter and hotter, it's impossible. So a cup of hot coffee doesn't get hotter in a cooler room. So this means energy has its value. Okay, like a hotter object, its energy value is higher. And also, when energy is transferred, always when energy in nature, when energy is transferred from one form to the other, some energy must be permanently reduced to a lower value. For example, like for forward heat engine power plants, we are using hot working fluid to produce work. Then it always needs to reject some heat at a lower temperature. And also, like this one, if we want thermal energy to generate electricity, yes, it's the same. we always also need to some energy will be reduced to the lower temperature value. And then you think, okay, because in nature we know the electricity, okay, can generate heat easily, okay, electricity, and heat is always transferred from the hot object to the low temperature object. Then we will think, can we make it happen? Okay, so like the heat, okay, we extract heat from the cooler room, okay, and provide heat for the hotter coffee. If we can make it, okay, thermal energy uh, transfer convert thermal energy to electricity. In nature, it cannot happen, but we have so during the industry revolution, so we invented heat engines. So heat engines can make this happen. Heat engines can make this happen. Okay, so so in the coming slides, in the coming several lectures, we will introduce the heat engines. So how the heat engines can extract heat from the cooler space and supply heat to the hotter uh, place, and how we can convert heat into power or electricity. Then we have to introduce heat engines. So because work can easily convert it to other forms of energy, but converting other forms of energy to work requires some special devices. The special devices called heat engine. So very lucky. So since the industrial revolution, we have the heat engines. We invented heat engines. So that's the reason we can we have moving parts. Okay, just like we have cars, we have steam engines, as we have introduced previously. So now let's have a look. What is a heat engine, and what kind of heat engines we have? And for heat engines, what is a heat engine? A heat engine is a system which operates continuously and across whose boundaries flow may only heat and work. So then we will think, okay, we think there is a system. Okay, there is a system. However, we think it's a closed system. Okay, closed system, and across its boundary, so the the flow is only heat and work. In general, we have two types of heat engines. They are forward heat engine and reverse heat engine. So now let's have a look at forward heat engine. So for forward heat engine, so be careful, here is small. The direction is really forward. Okay, so for this heat engine, it's a closed system. For forward heat engine, we know it's really is forward. So for the forward heat engine, and we have to learn two important terms, including thermal energy reservoir. So when we study heat engines, we always have the assumptions of thermal energy reservoirs. So what are thermal energy reservoirs? It means the thermal reservoirs which can supply or absorb infinite amount of heat without undergoing any change in temperature. So for the thermal energy reservoir, according its definition, they shall be with a constant temperature. With the constant temperature. And so we think for the thermal energy reservoir at a constant temperature, it can absorb heat, it can supply heat, okay? And however, at a constant temperature, if a thermal energy reservoir that supplies energy, okay, supplies energy in the form of heat, we call it a source. It's a source. The thermal reservoir supplies heat. If the thermal reservoir absorb heat, okay, then we call it a sink. So now let's determine so which one is a source, which one is a sink. Okay, so let's have a look at the forward heat engine. So we know there is some heat engine we invented. So for this heat engine, so across the boundary, only heat and work. Now let's see what's the heat and the work. So I use the red color to indicate the heat. So for forward heat engine, okay, there is a high temperature thermal reservoir. High temperature thermal reservoir. So because it's supply energy, so then it's a source. We call it a source. Okay, it's a source. Then let's have a look for the forward heat engine. In fact, as we remember, according to second law, so when there is any thermal energy, there is any energy conversion, then some energy will be deducted to a lower energy value. So in fact, then we will also reject heat to a lower temperature. So we called is okay. We are using L lower. So this is a sink because it absorbs heat. Okay, it's absorb heat. And for forward heat engine, as we just mentioned, we want to convert thermal energy. Okay, here is a thermal energy or heat. There is a heat flow. We want to convert the thermal energy into work. Then, in fact, we can see when the high energy value, thermal energy, and to lower energy value, then so for this process, in fact, some of thermal energy can be converted to work. Okay, so because the high the working fluid can experience expansion process. Okay, then there's work, and so this is a forward heat engine. So this idea is used for power generation and also for steam engine. Steam engines. So steam engines are very powerful, okay? Just like our cars and before the the trains, the cars, and all moving parts. Okay, usually is the forward heat engine. We want to make use of the work or uh, the work, and also we will introduce is mainly for the power plant. I think through our in-class quiz, we have understand that, okay, the energy transformation. So for a car, for steam engines, is steam engines. So we can see how a car work because we have the steam engines. So we can by combustion of fossil fuels from chemical energy to thermal energy. Okay, then the thermal energy experience expansion. So then we can produce work. We can produce work, and this work, if they can use to move the cars, the trains, and any moving parts, and also, in fact, for power plants, we can connect it to the to a power generator. Then the work can be converted to electricity. And so here is showing input. However, it indicates for me. For me, you can see the arrows are different, but although the arrow is different, and here, so we can see it indicates the values I with it's negative with -1, so we can change the we can change the direction of the arrow. Okay, so here is heat absorption. Don't worry because at the moment I just give a brief on the heat engines. Just we understand that we need some specific devices to convert so some energy to work, and also extract heat from the low temperature thermal reservoir. And we also have the other type of heat engines. They are reversed heat engines. So for the reversed heat engines, we can see that okay, so the direction. Okay, so the heat engine, the flow direction is reversed. So that's the reason it's called reversed heat engine. So very interesting for the reversed heat engine. So we can see is also here is the low temperature. The low temperature thermal reservoir, but it supplies energy. So this is the source. However, the low temperature thermal reservoir becomes the source. And then it rejects heat to the high temperature. So the high temperature becomes the sink. And for this reversed heat engine, in fact, it cannot happen in nature. Okay, because we know the heat transfer always from the high temperature object to the low temperature object. So therefore, we have to provide. So if we want to achieve this process to extract heat from the thermal and low temperature thermal reservoir, and okay, and then it's not for free because we need a reverse heat engine, and also for the reversed heat engine, so we can see it will need work input. This is reverse heat engine. What's the application is for our home air conditioner. Our home air conditioner, home air conditioner, home refrigerator, okay. Uh, a home refrigerator and heat pump and chiller. So if we mention, if then you will think, oh, this is a heat engine, this is a cycle, then how to carry the heat? So what's the working fluid? What's the working fluid in the heat engine? So we need working fluid to carry, okay, to carry the heat, absorb the heat from the source, and there is expansion and there's heat rejection. So what working fluids we need for our heat engines? So for forward one is usually is water steam. Okay, that's used usually for power plants and also for our steam engines. Okay, water steam. So we here water steam absorbs heat and then becomes steam. And then for the reversed heat engine, in fact, is refrigerant. So now we understand why last week we learned the properties of pure substance, and why I provide you the tables and the diagram for water, steam, and the refrigerants, because we will understand that during the process there is phase change, like here expansion and the rejection, heat rejection. Then the processes will experience phase change. If the working fluid in the system, okay, they are circulates all the time, okay. Okay, if like water becomes hot steam and expansion and water, then it's called thermodynamic cycle. So for a thermodynamic cycle, it occurs when the system undergoes two or more processes and returns to its initial state. And if it's for a thermodynamic cycle, we can think it's a closed system. It's closed system. So for the system, the change of internal energy is zero. Okay, that's when we apply first law of thermodynamics, we understand it. So for the application, just like if for steam power plants, so we first lecture we have introduced for steam engines, the energy transformations. And for steam plants, so we can see there is water pumped and absorb heat and becomes steam, and there is a turbine. So for the turbine, it can expand expand for the expansion process. If there is expansion process, there is a work output. If the work is by rotating shaft and mechanical energy power, so if connected to a power generator, if it's connected to a power generator, then it can generate electricity. Okay, so we will learn together. So it's for the working fluid is the steam, is water steam. The water steam receive heat from the high temperature source, and then through expansion process convert part of this heat to work. And we understand according to second law, some energy will be simultaneously converted to reduced deducted to a lower energy value. So we also will reject some heat to a low temperature sink. Okay, they operate on a cycle. The water steam, the working fluid operates on a cycle. So for the reversed heat engine, so for us to better understand, is our home refrigerator, air conditioner. So we extract heat, okay, for a low temperature source, although it's also it's I think we should call it a source because we extract the heat from the low temperature source and then rejected heat to a high temperature sink. Okay, but this heat engine is not free. We need it will consume work because we need to compress it from the low pressure to high pressure. Okay, don't need to worry because we in the future few weeks we will mainly introduce the heat engines, forward and reversed heat engines. Then, if we introduce heat engines, the special devices and the system, we always want to know what is performance, what's the desired output, what's the required input. Okay, so therefore, for forward heat engine, effect for forward heat engine, so we can see that we are using cycle efficiency to describe its efficiency. According to the for the cycle, the heat engine cycles its efficiency, how to determine its performance is we want to know what's the designed output, and then what's the required input. So for forward heat engine, so the designed output is the work, okay? Is the work because we want to convert thermal energy into work. The work can be used for steam engines to move to make our cars, trains run. And however, the required input is the thermal energy. Okay, is the thermal energy. Okay, is how much heat required for the forward heat engine. And what about the reverse heat engine? So because this is interesting, this cycle efficiency is much larger than 1. So that's the reason we cannot use the efficiency. We are newly introduced for reverse heat engine. We are using a coefficient of performance. So for the performance for refrigeration, we want to get the cooling. Okay, we want to know, okay, what's the design output? Is the cooling effect or refrigeration effect? And the required input is the work. Then for heat pump is for if it expects heating. Okay, like is for if we expect heating, that's a common in Hong Kong. We are using heat pump to provide to provide heat. So then V becomes this one. Okay, so I'm always asking you to understand. So for cycle efficiency, and this formula is very important because in the future, you know, we have different technologies. We have different technologies. However, how to examine is for the heat engine, for any system, its performance. We always using this definition equation. Is how much you desired and how much you have to provide the input. So, and then you see for this equation, we got a heat flow and heat flow and work. Then we need to understand their relationship. So for a thermodynamic cycle, so we know the equation, the first law equation for the application, then we can easily understand the relationship between heat and work. So let's see, like here, okay? So this is input, okay? This is output, okay? This is also input. So therefore, we know these two will be equal to these two, okay? So for our system, what's the input will be equal to the output. That is energy conservation. And also for the reversed heat engine here is the same. Okay, then how much supplied? Okay, in fact, this use like this. This is input will be equal to the output. So we have, I remember I prepared for 2 examples, so we will further learn. So how to, besides to calculate the efficiency, and also we need to know how to understand how to together applying first law. Okay, so now I have prepared 2 examples. So see what's the cycle efficiency and COP. Okay, maybe you spend a few minutes to see if you understand and do the calculation. Then after 5 minutes, we work on these 2 examples together. So for the question, firstly, you need to know if it's if it's a forward heat engine or reverse heat engine. And what's the expected output? What's the result input? Okay, read the question and do the calculation by yourself. So for 5 minutes. Okay, so now let's have a look. For example number 1, firstly, we need to know if for a heat engine, the cycle is forward end, because here indicates is forward. It's forward, and this one, we can see the direction is reversed heat engine. So for forward heat engine, then we understand that its efficiency, cycle efficiency, is expected output. Expected output is here. Okay, this is the expected output. Then it's not for free because you want to convert thermal energy into work. So therefore, we want to get the required input. This is the input. Okay, this is the required input. So therefore, it's 30 over 100. Okay, it's 30%. Is 30%. And for reverse heat engine, because this value in fact is larger than 1, so we are using COP. So now let's have a look at the COP value. So for the COP, for the reverse heat engine, we want to know what's the required what's expected output. So for reverse heat engine, then if we for refrigeration, for cooling, we expected output is the cooling is 70 units. Okay, is the cooling. And what's the required input? The input is the input. Okay, is here. The required input is 30. Okay, so then this is the result of COP. We can see the COP is larger than 1. And then what about example number 2 is a heat transformed to a heat engine from a furnace at a rate of 80 megapound. If the rate waste energy, so for this question, firstly, we can see this is a forward heat engine. Okay, forward heat engine. For forward heat engine, so heat transferred, okay, is 80 megawatt. And waste energy is 50 megawatt. Then what's the work output and the thermal efficiency? So for this one, we can see according to first law, then we get, okay, the input, the work output, in fact, is 30 megawatt, okay, because due to first law of thermodynamics. Then we can calculate the efficiency, okay, the efficiency is expected output is 30, okay, the required input is 80, okay, then you can get the value. You can get the value. So now we can say whatever heat engines, you need to know what's you expected, the expected output, and expected output, and required input. Okay, we have a 10 minutes break, then we come back to continue introduce the second law of thermodynamics. Okay, let me know if you get any question. Thank you. Okay, welcome back. So let's continue our lecture. We understand that in fact in nature, so there is energy value and energy quality. So for that energy transformation, in fact, since the Industrial Revolution, we invented heat engines. to make some energy transformations happen. So they are called heat engines. So now let's have a look the details of the second law of thermodynamics. So together with the first law of thermodynamics, the second law of thermodynamics states that whenever energy is transferred, energy must be conserved. Okay, this is the first law. But the value of energy cannot be conserved, and some energy must be permanently reduced to a lower value. So that's the reason you think if we want to, for the power generation, you think, oh, all heat, okay, can be converted into work. So it's perfect. Then your power plant efficiency is 100%, but it's impossible. Then we know that, in fact, and one of its important cases is in engineering is to determine the best theoretical performance of a heat engine. So like you think if all can be converted if for the transformation, because some energy will be permanently to a lower value, and so this efficiency, cycle efficiency, is impossible. If it's 100%, then it's impossible. Okay, now let's have a look and what's cannot observed. So in fact, the second law of thermodynamics gives us the direction of the energy flow. Okay, so not all thermal energy to work. And there is a long history, and because in the history, many scientists try to improve the efficiency and also want to, it's ideal. So all the thermal energy can be converted to work. However, Carnot firstly observed that in steam engines, no work could be produced unless there was a heat flow from a high temperature thermal reservoir to a low temperature. So only from there's heat flow from thermal energy, and also there's heat rejection to a lower temperature reservoir, then there is work can be produced. And also Carnot further noticed that the work produced was a function of temperature. So it's interesting. The efficiency is mainly a function of temperature difference between the high temperature and the low temperature. Okay, so this efficiency is only a function of the temperature difference, the two temperature, the high temperature and the low temperature of the temperature of the thermal energy reservoirs. And also, if these two temperatures greater, then for a greater cycle efficiency. Then similarly, we can find that with their other statements together with the Carnot cycle, its observation is the same. So it means so Clausium statement in 1950 is that if it is possible for any system to operate in such a way that the sole result could be an energy transfer by heat from a cooler to a hotter body. Okay, so it's also mentioned you cannot only heat transfer in nature is from high temperature body to low temperature body. If you want to have energy transfer heat from a cooler to a hotter body, it's impossible. Okay, and also for the Kelvin Planck statement, so for the forward heat engine, so similar to Carnot's observation, so we can see these statements, it's impossible for any system to operate in a thermodynamic cycle and deliver a net amount of work to its surrounding while receiving energy by heat transfer from a single thermal reservoir. So these statements are equivalent, and also its meaning. Okay. we know heat engine can have a thermal efficiency of 100%. Okay, if you don't have this one, impossible. Okay, when there is a energy transformation must from a high value to a lower value. So there's two corollaries of the second law. It means it is impossible to construct an engine and system to operate between two heat thermal reservoirs, each having a fixed and uniform temperature that will exceed the efficiency of a reversible engine operating between the same reservoir. So, and also for the reversible heat engines with the highest efficiency. All reversible engines have the same efficiency is when working between the same two constant temperature heat reservoirs. So it means it's only a function of the temperatures of thermal energy reservoirs. So we can prove it. Like if we are using reverse proof method, we can find the equivalence of the above two statements. So for example, if we assume a Clausium statement is wrong, so that there is a heat transfer always from a cold reservoir to hot reservoir. Then from the right side, and also from the right side, power also can be generated. Okay. For the combined system is the dotted line. We can see there will be power output from the single reservoir, and this result is against the Kelvin-Planck statement. Okay, so you can see if only pure work output and heat. And also the initial assumption must be wrong, so the Clausius statement is correct. So we can use the reverse proof method to prove that this is impossible. Okay, if there is only heat extracted from the cooler body to a hotter body. And as we have introduced from the Carnot and other statements, so we can see, but in the history, there are many scientists. They are working the perpetual motion machines. They think they can always operate. So the main two types of perpetual motion machines previously scientists, researchers, people want to improve. Like for example, the first type of perpetual motion machine. Okay, so let's see. So they think we still combust with the combustion of fossil fuels to no, not biofuel. They think there's a boiler is electric heater. So we heat the boiler, then the steam enters the turbine to generate power. And after that, so we will reject some heat to the environment. However, some of the generated electricity will be used to heat the water again. So for this one, they think if we can invented this machine, okay, we don't need power input, because for the heat engine, the produced work will be used to provide heat again. So for the system, only work output. Okay, there's only work output, there's only heat flow. So we can see this, in fact, it violates with the first law of thermodynamics, because our heat engine cannot create energy. So you just think we use the power electricity generated to produce heat again, then make this machine operates forever. to provide electricity, okay, without the consumption of any, without any input. So it's impossible. So for this first type of perpetual motion machine, is impossible. And then, in fact, people also tried to invent it, the second type of perpetual motion machine. They think, okay, I just want to convert all heat energy into electricity. Okay, then it's impossible because it violates the second law of thermodynamics. So it's with only a single thermal reservoir. In fact, with only one single thermal reservoir, it will not produce any work. So we can see, in fact, in the history, many people try to invent it, perpetual motion machines. So they think they can make the efficiency 100% or make they don't need any inputs, but we produce work. It's impossible. They violate first law or second law of thermodynamics. So they are impossible. So then we understand that, in fact, according to second law, any processes has its direction, and then when the energy transformed, also some energy will be permanently reduced to a lower energy value. And so together with the second law of thermodynamics, in fact, we have to introduce entropy. So because entropy is used to examine the disorder, thermal equilibrium, and the disorder of the system. And also we know the entropy for any isolated system, the entropy of a system towards disorder, towards increase. Okay, now let's have a look what is entropy. So entropy, as we have introduced before, it is a system property that would denote whether or not the system was in thermal equilibrium. And the definition of entropy was developed by applying the Clausius inequality to a cyclic process. So that's mainly if it's for reversible process, so the entropy can be defined by the change at a temperature, the heat absorption or heat rejection. Although for any, the entropy will decrease and also increase for the process if for a specific process, if the system receives heat. So now we have a video to help us in further understand what's entropy, how entropy can be used to donate the system thermal equilibrium and the disorder of the system.
Grammarly does more than catch errors. With Grammarly, you can find really good, no, perfect. There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other. Why ice melts, why cream spreads in coffee, why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it, and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between the solids has the highest entropy. So, in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out. To see why entropy is useful for explaining spontaneous processes like hot objects cooling down, we need to look at a dynamic system where the energy moves. In reality, energy doesn't stay put. It continuously moves between neighboring bonds. As the energy moves, the energy configuration can change. Because of the distribution of microstates, there's a 21% chance that the system will later be in the configuration in which the energy is maximally spread out. There's a 13% chance that it'll return to its starting point, and an 8% chance that A will actually gain energy. Again, we see that because there are more ways to have dispersed energy and high entropy than concentrated energy, the energy tends to spread out. That's why if you put a hot object next to a cold one, the cold one will warm up and the hot one will cool down. But even in that example, there is an 8% chance that the hot object would get hotter. Why doesn't this ever happen in real life? It's all about the size of the system. Our hypothetical solids only had 6 bonds each. Let's scale the solids up to 6,000 bonds and 8,000 units of energy, and again start the system with 3/4 of the energy in A and 1/4 in B. Now we find that the chance of A spontaneously acquiring more energy is this tiny number. Familiar everyday objects have many, many times more particles than this. The chance of a hot object in the real world getting hotter is so absurdly small, it just never happens. Ice melts, cream mixes in, and tires deflate because these states have more dispersed energy than the originals. There's no mysterious force nudging the system towards higher entropy. It's just that higher entropy is always statistically more likely. That's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will.
Okay, we just finished. In fact, it's to introduce what's entropy. I think it's in fact even there is books on entropy. They use the whole book to introduce entropy. It's very complicated. So we just have video even introduce us why the heat transfer from a hot coffee will get cooler, although there is a chance to get hotter and hotter, but the chance is too tiny. So we understand the entropy. In fact, for us, is to usually to measure the disorder and the thermal equilibrium of our system. And for entropy, is a property, and also we can trace it. And for the entropy, we can see, in fact, on the temperature, on the pressure pressure volume diagram, we can get the entropy curves. Okay, constant entropy curve. So entropy is also a property like enthalpy and other properties. So a system undergoes a cycle and developing a network output via drawing heat from a single reservoir at one fixed temperature. The cycle is impossible. For the previous assumption, it is against second law. And also, there is therefore, we can have the entropy line. So there's a property presented by reversible adiabatic process is entropy. So we have the entropy line on the diagram, because so if you have interest, you can see how property entropy is a property. We have the property line. And be careful, entropy only for reversible process. We can calculate the change of entropy. It's only for reversible process. It's only for reversible process. So for a reversible process, the entropy difference for a thermal process, we can calculate the change, the entropy difference, okay, for a thermal process from state 1 to 2. We can use this equation to calculate. So we can see this is for that thermal reversible process, the heat flow over its temperature. Okay, the temperature can be variable. And what about if it's a reversible, irreversible process? Then the entropy difference cannot be calculated, because we cannot use this equation to calculate the entropy difference, the change of entropy during a reversible process. It's larger than okay, than the change of entropy. So we can see for any irreversible process, the entropy change, okay, the entropy difference is larger than the reversible process. So we may reach the following conclusions regarding the entropy change of a system. For adiabatic closed system, adiabatic, that means is zero. Okay, is zero. For adiabatic closed system, it's zero. So the entropy will increase due to the internal irreversibilities. So for adiabatic process closed system, the entropy can be the change will increase. However, if it's reversible adiabatic process, for adiabatic process, so the entropy will increase. The entropy will increase. However, if it's a reversible process, then has the same entropy. So then, previously, I always mentioned if it's a reversible adiabatic process, it's also called asentropic process. Okay, asentropic process. So for this process, so we can see the entropy, specific entropy is same. So this is very important to understand because this is for any processes, okay? For reversible process, we can use this equation to calculate the entropy. However, we can see entropy is related to the flow, heat flow. If it's adiabatic, it means there's a heat transfer, heat flow is 0, so the entropy will definitely increase. If it's reversible, the change of entropy will be 0. And therefore, for all working distance, in fact, we are using differential entropy. Okay, this equation to calculate the differential entropy, and so for thermal process. Okay, for reversible process, we can use the equation to calculate the entropy change. And also, we can find the relationship between the change of entropy and the heat flow. So we understand that from state 1 to state 2, from state 1 to state 2 for any reversible process. For any reversible process, we can find the relationship. We can use the integration of temperature times differential entropy to calculate the heat flow. And so we just I think during last tutorial we have mentioned like on the temperature entropy diagram, if there is any process, okay, from any process from state 1 to state 2, okay, so the meaning of the temperature, okay, similar to the reversible work, okay, this the meaning is temperature times the differential entropy. So therefore, we can see if we get the integral, okay, we get the integral, then we get the shaded area, okay, the shaded area. So the shaded area can represent the heat flow, okay, it can be heat absorption or heat rejection. So that's the reason we also temperature entropy diagram is very popular because we can see we are interested in heat and also work. So therefore now pair up we have the similar formats of the calculation expressions for heat flow and for work. For work, is due to the change of its volume, okay? The change of the volume. And for the heat flow is due to the change of the entropy. So entropy, as we also introduced then, is we have proved that is a property, and there is for a reversible process, we can trace the change of entropy. Okay, we can trace the change of entropy, and also, so for how to find out the entropy, we know how to define if it's compressed or if it's superheated or is in the wet region or also or in the wet region. And also if it's in the wet region, we have to calculate the dryness fraction. Okay, the dryness fraction. After we know the dryness fraction, we can calculate all other properties. So therefore, in the future, we will know because temperature entropy diagram, we can directly understand the heat flow because the shaded area can represent the heat flow easily. So therefore, usually we have interest in heat and work. So in the future, we will find the temperature entropy diagram is very popular. So because we know two independent properties will define a state. So there's two. We remember there's any two independent independent property will define a state. So therefore, if the temperature and entropy together, we can also define the state. So in the future, we will know the temperature entropy diagram with two properties is very popular. So when we study the heat engines, so for the heat engine, the processes is very common. So let's have a look on the temperature entropy diagram, and also I also attached you some diagrams for for water steam and also for reference. So there we can see we still have the saturation line, and also we know the critical state, and also we see with the increase of the temperature, the horizontal distance gets shorter and shorter, which means the the specific enthalpy and the change of entropy gets smaller and smaller. Okay, and also we understand that from any process, okay, any process. So this area represents, okay, it represents the heat flow. So therefore, the integration of temperature times differential entropy will be equal to, for that process, what's the heat flow. Okay, it's with the increase of entropy, then it's if the change of entropy increase, then it's a heat absorption process. If the change of entropy decrease, then it's a heat rejection. Okay, we have to be careful to understand the increase of entropy. That means it's heat absorption process. If there is a heat rejection, then it's a heat rejection process. And we can see the different thermal processes and the different constant pressure can be described on the temperature entropy diagram. And we need also understand for different pressures. So we can see the distance of the horizontal line is different, okay, is different. Then let's understand, in fact, for this one, the difference, okay, is the this usually from the steam tables. This is, I think, a kind of a recap because we have learned. So when we introduce the tables and the diagram, so F usually means is the for the saturated liquid. Okay, here, this one. This use saturated liquid. Okay, they're using F fluid. Okay, that means this one. They're using the entropy. And here, this point, this saturated vapor, they are using saturated gas. Okay, it's the saturated vapor. Then this is the difference. And also we can see this difference gets smaller and smaller, okay? Smaller with the increase of the pressure. Then for the entropy of wet steam, it is given. And also we have assignment number 1. There is also one. I'm asking you to calculate through with the given entropy for the wet steam. We calculate its enthalpy. So I think you need to calculate the dryness fraction and then calculate the specific enthalpy. So we can see for wet with the dryness fraction, we always need to calculate the dryness fraction. Okay. Then the dryness fraction, if you with the given entropies, we can also calculate the dryness fraction. With the calculated dryness fraction, we can calculate other properties. We can find other properties. So on the temperature entropy diagram, so as I have mentioned, this is a heating process at constant pressure. Okay, this is a heating process at constant pressure. So from compressed for saturated liquid, then is wet, saturated wet, then superheated. Okay, and we need to understand. So for the heating process, the entropy will increase. And the dryness fraction, so we can see for this constant pressure heating process, entropy will increase. And for the dryness fraction, the calculation here again is also we can use the distance of F1 over the distance of Fg. So we can also use the distance ratio to calculate the dryness fraction. So we can say this is the distance F1. So if it's here, then it's 0 because this is 0. If we're here, then it's 1, the dryness fraction. So don't make sure if you with the given and from the distance ratio, we can also understand the dryness fraction. Okay, because the dryness fraction is also proportional to the distance of the state point from the saturated liquid line on the temperature entropy diagram. So the area under the line Fg, okay, this one, you can also consider is the specific enthalpy of vaporization, because this is according to specific enthalpy of vaporization definition is if we heat 1 kilogram fluid from saturated liquid to saturated vapor, the heat required for that process. And the area under line 1F is given by using the dryness fraction times the specific enthalpy. Okay, in fact, it's very interesting to understand the temperature entropy diagram, because on temperature entropy diagram, we want to observe the heating process or cooling process because it can represent the heat flow easily. Okay, for a heating process. Or for a cooling process. Okay, so for the heating process, in fact, we also have introduced during our tutorial session. So on the temperature of entropy diagram, this is a heating constant curve. This is a constant pressure curve. So this represents a heating process at a constant pressure. Okay, and we need to calculate the dryness fraction with the given one. Similar, we calculate the dryness fraction, then we can define state 1 is superheated or is in wet, and also if it's wet, we need to calculate the dryness fraction. And also we check from the table, this is superheated. It's superheated. And for state 1 is wet. And then we calculate, then we can use the dryness fraction, then we can calculate the enthalpy of state 1, our enthalpy of state 2. So for the heat flow, we can just use the enthalpy difference following the first law of thermodynamics. Okay, because there's for heating process no work. Okay, for this heating process no work, and then we can directly use the enthalpy. This from superheated steam table, this from the saturated table to calculate the dryness fraction, and also the based on the dryness fraction, we can calculate enthalpy. We have introduced in our teaching note. That's what we have learned today. Think to summarize, to conclude. What we have learned, then we understand that energy has its value and quality. So therefore, for all thermodynamic process, it has its direction. For example, heat transfer always from high temperature body to low temperature object. Okay, and here, so also through the introduction of entropy, there's also introduced why any thermodynamic process has its spontaneously has its direction. Okay, due to the introduction of entropy. And also for second law of thermodynamics, we have different expressions, and we also understand if because the thermodynamic process has its direction. So if we want to convert some energy to work, then we need heat engines. We need heat engines. And for heat engines, we had two types of heat engine. So forward one and reversed one. So for forward heat engine, we understand that is we need some device to convert heat into work. So that's very common for like for steam turbines, for cars, for trains, and for others, for airplanes, etc. And also for power plants. And we also have reversed heat engine, which can help us extract heat from a cooler body and to reject heat to a hotter body. And then we further understand, in fact, related to second law thermodynamics, we have to introduce entropy. So, and also we can see there is a relationship between the heat flow and entropy. Okay, so reversible for reversible process, therefore the heat flow for any process from state 1 to state 2, we can use this equation to calculate the heat flow. Okay, so we can see for a heating process, the entropy will increase. And then it's similar to work. So for the heat flow, it's mainly due to the exchange of entropy, then will related to the heat flow. Then what about work? So for work, so we can see it's due to the change of volume. Okay, due to the change of volume. Okay, the change of volume will cause work input or work output. See, if there's a change of volume is 0, then this work input or work output will be also 0. If for a system change of entropy is 0, so like for isentropic process, then there's no heat flow. Okay, so that's what we have learned. And also we have further learned on the temperature entropy diagram. We understand so for a heating process or cooling process, and the below shaded area and the process line is the heat flow. Okay, this is what we have learned today. I will stop recording now, and we still have a few minutes to see if you get any question. Okay, I know it's tough for you because the Chinese New Year is approaching. So I'm sorry we still have our tutorial session. So this Thursday, if you are busy with your family, you need to help them to purchase food or flowers for New Year. So you can just so watch the recording. So this Thursday. Okay, thank you. Uh, okay, thank you for your question. I think for the submission deadline, initially I planned it's 22, but I'm worried about after Chinese New Year, maybe some of you cannot submit. So I set it at 23rd. Okay, I think you just submit it before 23. It's okay. Okay. So in fact, originally I planned to set 22, but that's just after New Year. I'm worried about some of you will miss the deadline. Okay, thank you for your question. 23 is okay. Okay, thank you. Thank you.